And it's recording, making sure I'm recording from the right device. Okay. And that's recording just fine. Okay, so we can go ahead and get started with this class. Okay, are there any questions from last class about a homework assignment? I got a few people, like about 5 people, who consistently could not go from cannot authenticate to the virtual machine from WinSCP. Is that still a problem? Is still persisting?
Yes.
Yeah.
Okay.
I couldn't get it, and I went to the lab,
Mm-hmm.
and the people over there didn't help me. Like they didn't install my machine.
Okay.
Like I used it over there, and it still wasn't working for like almost like a half hour.
Mm-hmm.
I had enough time to finish it out.
Okay. Because
And
last...
from the library and work from the IRC's machines.
Yeah, it is strange.
Yeah.
Okay. Well, if you have problems with that, bring your virtual machine to the lab today, so I can at least take a look and see if I can figure out why it is not authenticating. You had a question, sir? Well, there may be problems, but one problem may not be the same as the next problem, even though they're all kind of reported as not authenticating. Because if the virtual machine is not running, there's nothing to authenticate against. So that's one problem. And then the second thing is, which account are you authenticating against? Which account are you logging in as? If you try to log in as the user, it won't work because the user does not have a password. There's no way to authenticate, as the user, the generic user. So you have to authenticate as your own username, which is the only account that actually has a password already set up. Okay, are you guys kind of getting the idea? So there are several steps, and if you miss any one of those steps, it will still kind of be reported as access denied or authentication failed or something like that. But the reason why it's reporting that problem is different. Okay, are we doing okay so far? This is not a networking class, so I don't want to spend too much time to talk about how the networking part of the virtual machine is set up. But in the class, last time I did kind of demonstrate that I could get it done or get it working in Windows 7. So I know at least with this machine or the way Windows 7 is set up on this machine, I do not have any problem. I tried the same thing on my laptop computer, which also has Windows 7, and I did not have any problems either. So the issue can be a configuration-based issue. If you run a software firewall, I'm just saying that because I know some of you have already tested and turned off the firewall, and the same problem occurs. So I'm not quite sure why, until I have time to actually look at your particular setup, I cannot pinpoint the problem. Okay? How many people did not have any issues whatsoever? You can kind of get it all done. Are you guys all using Windows 7 too, or using a different version? Okay.
I tried a Mac and Windows 7 had no problems, and the cisp Linux.
Okay. I know it should not be an issue in Linux, unless you have firewall rules.
Make sure it works.
Right.
I'm always switching operating systems and stuff.
Okay. So for the people who cannot get it working, I will spend some time in the lab tonight. If you have your virtual machine with you, I will go to the lab, using your virtual machine, and see if the problem can be replicated. And I want to figure out why it is happening also, because I don't want the same problem to happen again. Okay. Any other questions? Any other issues? No? Okay. All right. So as promised, okay, this is not the right class, I think. Yeah, we don't want to go back to cisp310,
Probably will be. I don't know, that class might be too hard for us.
Well, I don't know, because the way I teach cisp300 is actually closely related to this class. For those of you who took cisp300 from me, you remember, how we set up the return address, the parameters, and also the variables, and we keep, creating new stuff using new columns. You will see that again in this class, except we don't use columns anymore. We are using the stack instead. So all those concepts will actually come back from cisp300 in this class. It's just that the names are now different. They are no longer called columns. They now have a different name. So we'll get to that stuff maybe in the middle of the semester or so. But as promised, I have a sample program called bad return written. It is completely handcrafted. Okay, I know this is completely just handcrafted, but it will display the symptom that I talked about last time. In other words, main will call subroutine F or subroutine G, and then subroutine G will return to subroutine F instead of main, and then the program crashes when it tries to return from subroutine F. Okay, so let's go ahead and take a quick look at this program, and I'll run it just to be sure that it still crashes the way it's supposed to. This is the program, okay, and I am a C programmer. I'm not a C++ programmer, and as a result, I use standard I/O instead of the streams, I/O stream. I have a function called G here. Yep.
Can you make it bigger, please?
Yes, I can.
Thanks.
I have a subroutine called G. G is definitely not good. Okay, you can see that it has a local variable as an array X. X has 4 bytes, 4 characters allocated, and I'm accessing the 9th character in the array. And I'm changing it to some pattern, hexadecimal D0. I have a function f, which is completely normal. The only thing it does is to say, this is weird, because guess what? Nowhere in this program am I calling f. In other words, if the program prints, it is weird, this is weird, it is in fact weird. All right? The main program doesn't do a whole lot. It calls the subroutine G, and then if subroutine G comes back and then it prints this is not so weird, it is not so weird because that's exactly what we expect the program to do. Return 0 because it is a function that is supposed to return an integer. So we know this program has a problem because I am accessing an array out of bound. The question is, what is the behavior of this program when it runs? So let's go ahead and give it a try. And what I'll do is the usual stuff. This is a useful technique. Copy, just like, copy, Control-C, switch to a terminal. I think this is too big because I can't see the entire thing. I will go ahead and create a folder for today, 2011. This is 0125 cisp310. Go to that particular folder. And I will create the file, badreturn.c. This is the same technique that I used last time. I am using cat to copy from quote-unquote the keyboard to a particular file. It is redirecting the output to a file. And then at this point, I can paste. I can either go to edit and paste, or I can just type the middle button. If you click the middle button in Linux, it is pasting the content in the clipboard. So either way would work. Okay. So here I pasted the whole program. It's ready. It's done. You type Control-D to mean end of file. End of file in Linux is Control-D. In DOS, it is Control-Z. Okay. Just in case some people have experience with DOS and want to know the equivalent in Linux. Now, I'm almost done, but I want to make sure that this is in fact the program that I am dealing with. So I'm going to go back, look at the program again, and this time using Vim. Everything looks right. If I want to turn on syntax highlighting, I can also turn on syntax highlighting. Nothing seems to be out of the ordinary. I think this program can be compiled. So to compile, I use GCC -o, just name the executable also bad return. I will give it the file name bad return, but I will also give it one additional flag, which is -g to include the debug information. It's probably not needed, but I'll just go ahead and include that anyway. And then I'll give it the source code file name bad return.c. So this is how you compile a program in using the command line. GCC is the name of the compiler. -g means I want to include all debug information so I can use the debugger. -o followed by the file name means I want the output, the executable, to be named bad return. And the last one is the source file. bad return.c is the source file to be compiled. Run the program. It does not find any problems, and now I can run the program. /bad return, and it says this is weird. It does not even crash. Okay? So something is odd about this program, don't you think? I mean, let you look at the program again. Don't you think it's kind of weird? I mean, it doesn't crash, okay? It's supposed to crash because I'm accessing an array out of bound. It did not crash. But it did something that's even worse than crash. It would have been better if the program just kind of crashed. Because it did not crash, instead of returning to main, G returned to F. So when you're debugging this program, okay, if you write a program not like this, but let's say a 5,000, 6,000 line program, and it behaves kind of like this, you won't even catch it. Most of the time, you won't even catch that it is returning to the wrong place. Okay, and your program is just misbehaving, and strange things starts to happen. By the time the program does crash or shows any type of symptoms, it's already way too late, because what is the one line that is the problem? The one line that is the problem is this line. The symptom in this program, which is completely handcrafted, shows up pretty much right away, because when function G returned, it returned to F, and I made F report this is weird. But in a real situation, the function that G returns to is probably going to be completely silent. Okay, has no indication that it is not supposed to get there. And that will continue to return and do some other stuff. By the time this program crashes, it will be way past the highlighted line, which is the source of the problem. Okay, so that's one problem. The second problem has to do with when someone who only knows high-level programming, like C programming, Visual Basic programming, look at this symptom, they don't even know where to start. Right? You don't even know, people won't even know where to start, which is a bigger problem. Okay? So that's why we have this class. Okay? This class will teach you assembly language programming, which means by the end of this semester, you will be able to write programs completely in assembly code. But out there, with all the different jobs, the actual number of jobs that will require you to program in assembly language is not really that much. Okay? So the value of this class is not that you can write programs in assembly language. The value of this class is you can look at C and C++ programs using X-ray vision. Okay? When the program does not behave, you don't just look at the patient and go like, you don't look well. Okay? Or, I think you're going to die. Stay away. So instead, you're Superman and you have X-ray vision. And you go, well, I think your lung is not too healthy. Well, from the looks of it, you probably have, tuberculosis, and, I know exactly how to treat that. So that is the value of this class. You will gain the X-ray vision, out of this class, and when you encounter symptoms that previously are uncurable in a C program or C++ program, after you take this class, hopefully the same type of symptoms will not stop you anymore. You will know where to start. You will know I'm probably accessing an array out of bound. Now that all by itself will help you locate the problem. Okay, it will help. It does not point you to the problem or the source of the problem right away, but it is one step to the right, one step in the right direction. So are we doing okay so far with this? Yes?
Don't the compiler do that for us already?
Well, I just ran the compiler. Right?
And you use another C++ and you compile and then looking for where the syntax error.
There's no syntax error. This program is syntactically entirely correct. Otherwise, GCC would have yelled at me and go like, no, this is not going to compile. So this program is entirely syntactically correct. Yep.
How do you get it to skip this is not too weird and then?
Sorry?
How did you get it to skip the printf of this is not too weird?
It did not skip that. It actually returned to F, and then F returned all the way out of the program.
It returned out of the program.
It returned entirely out of the program from F. It did not continue execution whatsoever after the call to G.
So it didn't come back to that point. He didn't come back to main.
It did not come back to the right point. Exactly. That was the problem. Yep. Go ahead.
Arguments go in main, like when it says in main.
Main does not always need an argument. Main needs an argument only if you want to interpret the command line options that you pass to the program. Are you talking about ARGB and ARGC? Argument count and argument array? Yeah, those are optional. I don't need this program to interpret the parameters. So as a result, I don't need any parameters with main. Okay. So this may seem a little mysterious, at this point. You know that something is wrong with the highlighted line, but you cannot quite explain why it causes the symptom that we are seeing. By the end of this semester, hopefully, every single one of you will look at this program again and say, that's nothing. I know exactly what's wrong with this program and why it is like this.
Is a final question?
I think as a final question, I will ask you guys, to write a program with a particular symptom instead. I give you the symptom. You give me the program that has a problem. That would be a good one. I've never asked that type of questions before.
I don't think you should stay.
Note to self. Okay, well, this is just a motivation to all of you and say, well, why do I want to take a class in assembly language programming? Because this is so archaic. Nobody programs in assembly language anymore. Well, this is why.
Because it's too hard.
It is not hard once you organize, okay? You think about, assembly language programming like, I don't know. You look at, the human body or just about any, high-level organisms, okay?
C is more fluid. Like you can tell what C is or C++.
C looks at things as a high level. In other words, it looks at a person and go like, oh, there's a head, there's a body, 2 arms, 2 legs, and stuff like that. Assembly language programming is looking into each individual cell. You're looking at the cells, and then you say, okay, we know this cell, now how do we make an organ out of these cells? Okay? But the beauty of assembly language programming is you start small, but if you know how to structure your program, you build up bigger blocks and bigger blocks and bigger blocks, and before you know it, you can actually write fairly complex programs in assembly language. Recursion is not a problem in assembly language programming. Okay? It's the same way that you write recursive programs in C. Exactly the same way. Assembly language programming is tedious, but if you structure and write your programs in a particular way, they're not really too bad. They're not difficult to debug, okay, because you can always debug modules by module. So you still have to use the same approach that you use for high-level language programming. The only time writing programs in assembly is difficult to debug is when you write your own real-time kernel. In other words, your own operating system. That is the only time, when programming in assembly can be a little bit difficult because you don't have an operating system. You don't have a debugger. You are directly on top of hardware. Okay? You don't even know whether your program gets to a certain point or not unless you turn on an LED. Okay? So that's the sort of thing, that... Okay, let me just... This is a little digression, meaning that it is not going to be in the exam unless you guys want to. We can always arrange that. So if you go to my website, and go to develops, and this is a real-time kernel that I wrote. Some people, knit, some people fish, and I just like, writing operating systems. So this is the operating system. It's a multi-threading operating system. And it has time slicing. It has all these features. These features you will see again when you go to a 4-year university and take their operating system concept class. You will see every single one of these again. Okay? And this entire thing was written in assembly. The code when you assemble this program or when you assemble this real-time kernel, it takes up 2 kilobytes. It's not a typo. It's not. I did not misspell it. It is 2 kilobytes, not 2 megabytes. 2 kilobytes, like as in 2,000 bytes. Okay, and it has all these features, and it runs on an 8-bit processor running at 16 megahertz. It would be suitable to put it into, say, a small robot, because it supports multi-threading. It has time slicing, which means you cannot have one thread hogging the processor. You can say each process or each thread can only take the processor for 5 milliseconds. After 5 milliseconds, you move on to the next available thread at the same priority level. Okay, so when you're writing programs like this, then I would say yes. Things do get a little bit more difficult because you cannot run GDB. This program runs directly on top of hardware. So the only tool I had to debug this program was 2 LEDs on the circuit board. Did I get here? Yes. Okay, good. But the program is still not right. So then you move that point, you move the LED turning code somewhere downstream and say, let's run the program again. Did I get there? Yes, you got there. That's it. The only confirmation is whether you got there or not. Now, since I have 2 LEDs, I can actually see, I can move 2 points at the same time. That was it. Debugging using an LED when you're writing programs entirely in assembly language. It was fun. I kind of like doing stuff like that. Okay, so let's go ahead and talk about binary numbers, additions, and subtraction. Because in this class, we will use binary numbers and hexadecimal numbers a lot. Most of the time, we try not to use base 10 numbers. Tell me again why we use base 10 numbers. That's the only reason, right? Okay, now have you guys taken a class that talks about binary numbers or base 8 numbers and stuff like that? Which class is that?
It was an assembly language.
Okay, but you took that class somewhere else?
Yeah, somewhere else.
Okay.
Not here.
What about the rest of you who took classes from here?
I took logic in high school, or in high school.
Okay. So they taught you, they talk about how to do base conversion?
Yeah.
Okay.
So it's 440 here.
Okay, 440, but not everybody has taken 440 before this class. Okay, go ahead.
Actually, do a pretty good unit on that MIDI programming or MIDI keyboard stuff.
Oh, okay, with the electronics technology. Okay.
Well, no, in music.
Oh, music. And they do base conversion in that class?
Or MIDI, yeah. Because we debug on MIDI players.
Oh, okay. That is so cool. Did they talk about LMMS? They do. Okay, I have to hook up with those people. Because I actually have LMMS, installed on this live Linux distribution. So, if you guys are bored, I can play techno music in the background for the entire class period. I don't think that's going to be distracting. It's going to be, soothing. Okay. So how about the rest of the class? How many people do not have any exposure to base conversion, stuff like that, binary numbers? No one. So that means I can ask questions about that right away. Okay, let's do it. I don't know. Let's try 481. What is the binary version of 481? This is a base 10 number. What is the base 2 representation of 481? Without using your calculators. My 5th grader can do it with a calculator. Without using a calculator, just go through a few steps, okay? I don't need the whole number, just go through a few steps. Give me the most significant 4 bits of this number. That's quick. I don't know yet. I haven't done it. Okay, so I'm going to do it, except I'm not going to do it on the whiteboard. I will do it, using a notepad. So this way, the video capture will also capture the entire process. If you guys like this approach, you should tell all your other professors to start to do it. because it's not difficult. Okay, all I have to do is to stay off the whiteboard and use Notepad or something, some tools like that. Okay, so the number is 481, and we just have to pick the largest power of 2 that is less than or equal to 481. Which power of 2? 256. Very good. So this is 256 plus what? My arithmetic is really crappy, so 225. Is that right? Hmm? 225? Okay. Okay, so now we have to break up 225 into a power of 2. So 256 is already done. What is the largest power of 2 that is less than or equal to 225? 128. Okay, and the remaining portion would be, I hate arithmetics. It's 97. Is that right? No. Yes? Yes. Okay. Okay, so now we have 256 plus 128, and then the next one is going to be 64 and 33. Oh, I picked a particularly interesting number, didn't I? 32 plus 1, and I have to repeat the last step on its own because I have to say that 1 is the largest power of 2 that is less than or equal to 1 itself. That's why I need that one extra step. So now I can convert everything into binary. What is the binary form of 256 in decimal? It is 2 to the power of what? Well, let's do this. Let's say this is 2 to the power of 8, right?
Yep.
Plus 2 to the power of 7, plus 2 to the power of 6, plus 2 to the power of 5, plus 2 to the power of 0. Very good. So now, if I use the binary representation, how do you represent 2 to the power of 8 as a binary number? 1 followed by 8 zeros. 1, 2, 3, 4, 5, 6, 7, 8. How do you represent 2 to the power of 7? 1 followed by 7 zeros. 1, 2, 3, 4, 5, 6, 7. And the same thing, 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, plus 1. It makes sense. Even the 1 makes sense because it is 2 to the power of 0, and therefore there are no zeros to the right-hand side. Okay? And of course, once you add these numbers, it becomes, just 1, 1, 1, 1. Like that. Is that right? 1, 1, 1, 1. Yeah. It looks right to me. Okay? So that's base conversion. I don't even need division. Did you notice that I did not do any division? All I have to say is to find the largest power of 2 that is less than or equal to something. Okay? What about conversion to other bases? Can you guys do that too? Conversion to base 3 maybe? It's easy.
It'll be the
Let
same.
me
It'll be the same. We find the power for.
Exactly.
Yeah.
So, okay, let me ask you this question. Some of you have doubts about whether you can convert to base 3 or base 7, some really odd, strange base. Do you think you qualify to work at McDonald's? Can you figure out changes? Like if someone, buys a Happy Meal for, I don't know, $6.59, $6.58, okay, and give you a $20 bill, can you use the least number of bills and coins as change? You think so? Well, then you already know base conversion. In general. Now, do you know why I said that? Let's look at the United States currency system and look at those values. Okay, what do we start with? Well, we start with 1 cent, which is 0.01 of a dollar. What is the next one? A nickel. Let's just go for the common types. Okay, then we have a dime. Then we have a quarter, $1 bill, I know there are $2 bills, but they are not common. So the next one is $5 bill, $10 bill, $20 bill, $50 bill, $100 bill, and so on. I don't see any regularity in here. Okay? Jump from 1 to 5 is a 5-fold increase, 5 times, doubling. 2.5 times, 4 times, 5 times again, twice, 2 times again, 2 times again, 2.5 times, and once again, twice. There's no specific pattern, and yet you can deal with it, right? So if I give you a different currency system, like this, I don't know, let's deal with base 5, okay? Base 5 is easy, because with base 5, I give you a currency that looks like this. I give you this, I give you this, I give you this, 5, 25, 125, 625, and so on. In other words, in a base 5 system, the currency will have one coin representing 5 cents, one coin representing 20 cents, one bill to represent $1, $5, $25, $125, and $625. Well, I like this better. It is a whole lot more regular. But yet you can deal with this already. What makes this more difficult? Yep.
Point 2 out of place.
Sorry?
Point 2.
The point 2 is, you're right. I should have made the last one 0.04. You're right. There we go. Very good. You guys caught me again. But the point is, if I give you a currency system like this, it is actually easier to work with because, it is just times 5 to get to the next level, right? Now, let's go ahead and give it a try, okay? Oops. Let's give it a try. Let's say we want to make a change, figure out the change for $65, and I have to be careful here because some numbers may not be representable using whole numbers here. So I have to give you something that can actually be done. Okay, how about this? How would you represent $65.28, but only using a currency like this? Well, we always deal with the largest number first, right? So then you say, okay, let me just copy and paste this. This is really easy. Okay. Do I need any $25 bills? How about 125? How about 25? 2 of them. And after 2 of them, I will have $15 and something left. So we'll end up with 3 of these. And we don't need any one of these. We'll need 1 of these and 2 of those. That's base conversion. Oh, but wait, Tech, where's the base 5 number?
00231.
Exactly. That's my base 5 number. It's 230.12. Not only have I done base conversion, it is a conversion with a fractional part as well. That's not difficult. Okay? Are you guys now feeling confident that you can do base conversion? If you know how to make change using the least number of bills and coins, you know your base conversion already. You know more than base conversion. Yep.
Excuse me. You told that this currency, the base is 5. Yes?
This is base 5.
So when we have base 5, can we use 6, the digit 6 we cannot use?
You cannot use the digit 6 when you're dealing with a base 5 system.
Okay.
So when you write this number out, you don't really have 6. You have 00230.12. That's a base 5 representation of what we know as 65.28. Okay?
Why can't we have 6?
Well, it's like in a base 10 system, we don't have a single digit representing 10. We have 0 to 9. Okay. Very good. So we know our base conversion now. Now let's go back to base 2 and let me explain why. If I were to become a politician, the first proposition I would push is to teach binary numbers in elementary school.
Why?
Okay, because I think I will gain a lot of support this way, and I will become a good politician, and the big oil industry and the cigarette industry will pick me up in no time. I'll be rich, I'll be powerful, and I won't have to teach classes anymore. Yes?
But the other politicians wouldn't be able to understand the numbers you're using.
Even better. Now I can pass budgets in record time.
Or at all.
Or at all, yes. Things can actually be done this way. Okay, so let me explain why I want to push, why we want to do binary numbers in elementary school. Think about it when, kind of go back in time and think about how you learned multiplication in elementary school. I think in most countries, including the United States, we probably learn multiplication in second, third grade-ish, about fourth grade, before around fourth grade. What is the difficulty of learning multiplication? The concept is easy, okay? Everybody has 4 candies. I got 5 friends, so together we have 20 candies. The concept is easy, but associating 4 times 5 is 20 is not easy because it's memorization, okay? It's pure memorization. 4 times 5 is 20. 5 times 5 is 25. 6 times 7 is 42, and so on. That's all memorization. It's rote learning, okay? There's no logic in it. It's just rote learning. But why is it difficult? Because we have base 10. That's why. Now, if you think about base 10, what is the matrix of the multiplication table in base 10? Okay, you have 0 to 9 and 0 to 9. Okay, some people will say, "Tag," but that's easy because the 0 row or the 0 column and the 0 row, they're trivial. Anything times 0 is 0. 0 times anything is 0. Okay, I will take that. Okay, the 1 is also easy because 1 is the identity of multiplication. 1 times anything is that 1 anything back. Fine, we take care of those too. Okay. And then someone will say multiplication is commutative, which means x times y is the same as y times x. Fine, we'll take that too. Okay, you're still left with this number of items to memorize. Is that right? Okay, and there's no quick way to get through this, other than just doing a whole lot of exercise, to memorize all that stuff. What about binary numbers? Give me the multiplication table of binary numbers. 1 times 0. Okay, let's start with 0 times 0 is 0. 1 times 0 is 0. 0 times 1 is 0. 1 times 1 is 1. I'm done. I have memorized my multiplication table. Right? The multiplication is 2 by 2, okay? And they all make sense. There's no memorization involved. But someone may say, but what about adding and subtracting? Okay, because we have to spend a lot of time to do adding and subtracting. Okay, 13 minus 7 is 6. But how do you know that? Well, initially we all have to count fingers, but at some point, it becomes memorized. And then we just say, okay, 3 minus 6 is 7 with a borrow. That's how I see subtraction. Let me say that again. 3 minus 6 is 7 with a borrow from the next digit. That's how I see it. The way this is represented makes it so that it is cascadable. In other words, using this way of looking at subtraction, I can now cascade everything. I can do multi-digit subtraction. It's 13 minus 6, but this is 3. It's not 13. It is really just 3. So if you look at just one digit, forget about the 1, the 10, it becomes just 3 minus 6. And 3 minus 6 is 7 with a borrow. If the next digit turns out to be 1, then the borrow and the 1 cancels out, and then the result becomes just 7. Okay? But there's a whole lot of memorization right here also. Okay? The memorization table is worse than this because subtraction is not commutative. X minus y is not y minus x. Okay? So this table is bigger than the multiplication table. And yet, we figure out, okay, we were able to memorize the whole thing. What about the subtraction table in binary? Well, let's start with the easy one. 0 minus 0 is 0. 1 minus 0 is 1. 1 minus 1 is 0. The only one that is odd is 0 minus 1. But using the same way of representing subtraction or the result of a subtraction, 0 minus 1 is nothing other than 1 with a borrow. Right? It's just, 0 minus 1 is 1 with a borrow. Which means, using this, I can now also cascade and have multi-digit binary subtraction. Okay? Let's do it. Let's go through a few examples. Okay? I'm just going to randomly pick some numbers here. Okay. And the way I do this, this is how I do it. I use one particular row for the borrow alone. In other words, this is the borrow row, and this is the final answer row. Okay. So, what is 0 minus 1? Well, first of all, do we have a borrow from the previous digit, from a less significant digit here? We don't, because this is already the least significant digit. So you automatically put a 0 here, because the first column, or the rightmost column, the least significant column, does not have a borrow because this is the column that we start with. That's why we do not have any borrow from any less significant digits. So what we do is we say 0 minus 1 is, according to this lookup table here, 0 minus 1 is what? Is 1 with a borrow. Are you guys seeing how I use the borrow? And then I have another subtraction here. Okay, this is also a subtraction. In this case, I have 1 minus 0. Using a lookup table here, 1 minus 0 is 1. Is that doing okay so far?
Could you repeat the last step with the borrow?
Okay, I wish I can TiVo my own recording, because then I can just go to the remote control and bloop, 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 and then it will just redo everything that I just did. But I can't, so I have to do it again, which is difficult because I can't really redo things easily. Okay, okay. So forget about this. Let me just erase everything and then start it all over again. That's the only way you can do it. Okay. Can everybody understand why I put a 0 here? There's no borrow from any less significant digits. Yep.
Excuse me, the fourth one doesn't make any sense to me because
The fourth one?
Yeah, 0 minus 1, 1. Because if we borrow 1, the 0 is going to become 1. So
It's a
1
borrow
minus
from
1.
from the next significant digit. It's just like in base 10, this is in base 10. In base 10, 3 minus 6 is 7, but with a borrow from the next significant digit. Okay? Are we doing okay so far?
Yeah.
Okay. So you're just pretending, if the next digit cannot be borrowed, if the next digit is a 0, then we keep borrowing until, we have something that we can either borrow or we just, say this is a negative number in the end. But are we doing okay with this here, with that 0? Because we don't have any less significant digit that can be borrowing from me, which is the least significant column. So now we just look at these two numbers. We have 0 minus 1. 0 minus 1, according to this table, is 1, but with a borrow from the next significant digit. I don't know whether I can actually borrow something, but I would just say that I need to borrow something from the next significant digit. And then we have 1 minus 0 here. 1 minus 0, according to this, is just 1. Is that okay? I'm not doing anything that involves thinking. I'm just doing mapping here. I use this lookup table to tell me what is the result, does it end up with a borrow? That's all I'm doing. I'm just applying those rules blindly. Let's deal with the second column. 0 minus 0 is what, according to the table?
0.
Just plain old 0. And then we have 0 minus 1 is 1 with a borrow. Is that okay? Now we have 1 minus 1 as a result of 0. And then we have 0 minus 1 with a result of 1 with a borrow. Now we have 1 minus 0, which is 1. And then we have 1 minus 1, which is 0. Okay? That's how we do subtraction in binary. And I would argue that this is a whole lot easier than subtraction in base 10. Because the only rules that you have to remember are these 4. Of these 4, the first 3 are trivial. Is that making any sense so far? Okay. Let's think about addition. In binary, 0 plus 0 is 0. 1 plus 0 is 1. 0 plus 1 is 1. 1 plus 1 is 0 with a carry. Is that making any sense? Especially the last one? Because we can always flip the logic of the base 10 example. In other words, I can ask you what is 6 plus 7 in base 10? Well, most people will say it's 13. But 13 doesn't mean that I can use this technique to have multi-digit addition. So instead of saying 6 plus 7 is 13, I say 6 plus 7 is 3 with a carry. Then I can stack up all these columns and have multi-digit addition. In other words, I'm doing all the things that we learned in 3rd grade, except I look at things from a slightly different perspective, just presenting it in a different way. Okay, so let's go ahead and do another example, but in addition in this case. So this time we have, let's say, 1011 plus 10010. Okay. And once again, we have 2 rows. One row is dedicated just for the carry. And then we have the final answer in the last row, just like before. And I think this is where watching the video clip will be helpful, because you actually see the action. You can see how the digits got filled in the calculation. I can write the instruction or in text all I want, but I think an animation of this is much more effective when it comes to understanding what is happening when we carry out the calculations. All right, so the first thing we do is we know we don't have any carry from any less significant digits, because this is already the least significant digit. Are we all convinced that we can put a 0 here? Okay, very good. So now we just apply the rules. 1 plus 0 is 1. According to this rule, 1 plus 0 is a 1. So that means, this one here, by default, is a 0. If I don't say it is a 1, then it is a 0, which makes sense, okay? The carry to the next digit is a 0, unless there's really a carry. Now we have 1 plus 1. According to this, 1 plus 1 is 0 with a carry. Now we have 0 plus 0, which is just 0 itself. We have 0 plus 0, which is 0. 0 plus 1, which is 1. And since neither addition generates a carry, the carry to the next digit will end up to be a 0. Now we have 1 plus 0, which is a 1. And then we have 1 plus 0, which is also a 1. Okay? Are we doing okay so far with the binary addition? Okay, we're doing okay with this? Okay. Can we do all this using logic gates? Okay, what kind of logic are we talking about? You guys have all taken C, so you know what is an and, what is or, and also what is not. Okay. But those things apply to Boolean values, not zeros and ones. Well, we can easily apply that to zeros and ones. So let me go ahead and quickly define what is AND in the context of binary numbers, and OR as well as NOT. Okay. AND is easy. 0 and 0 is 0. 1 and 0 is 0. 0 and 1 is 0. 1 and 1 is 1. In other words, 0 is false, 1 is true. Okay? If you want to do it with OR, just as easy. 0 or 0 is 0. 1 or 0 is 1. 0 or 1 is 1. 1 or 1 is 1. And then we have NOT, the negation. Negation is even easier because you can say not 0 is 1, not 1 is 0. Do we have any questions about these logic operators applied to binary numbers? No problems? Okay, very good. So now we want to go back and look at addition and say, can we do something about that? In other words, can I name this digit x, I name this digit y, can I come up with a logic equation to come up with the answer, as well as whether there's a borrow or not? That's the question. Let me repeat that question. Okay, let me just go back here and just we'll look at subtraction first. I'm just copying and pasting down here. And instead of using a subtraction here, I'm just giving you a table of outcomes. And also, we need one more for the borrow. If there's no borrow, I can also say there's a borrow of 0. Okay? Borrow of 0. Oops. Borrow of 0 and a borrow of 1. And I will name this x, I will name this y. X and y are my input into the system. This is my difference, and this is my borrow. So I will just go ahead and give you a key. X and y are inputs, D for difference, and B for borrow. And the big question is, can I apply logic gates to come up with D? Can I apply logic gates to get to B? Well, let's think about it. When do I get D to be 0? When both of them are 0, and also when both of them are 1s. Is there a way to use logic gates so that D can be expressed as yada 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 using X and Y with a bunch of logic gates in between?
X or Y.
X or Y.
For D.
What about this? X and not Y, or not X or Y. Would that do the trick? Well, the nice thing about binary values is it's easy to prove things. If I want to prove that D can be defined this way, it's easy. All I have to do is to apply all 4 possible combinations of xy to this equation. If this equation ends up with 0, 1, 0, 1, then this equation is implementing the D bit. Is that making any sense? So let's go ahead and do it. So what I will do is I will take this equation here and make it its own column. And this time I will go ahead and evaluate based on x and y and figure out the value of this equation or of this formula. Of the first row, x is 0, y is 0. Okay? When x is 0, then the conjunction is automatically 0, right? Because you only need one side to be a 0 for a conjunction to become a 0. And that applies to the other one too, because y is 0 as well. So we know that 0 or 0 is already 0. Let's take a look at the first row. The first row has x being 1, y being 0. Okay, let's deal with it. X is 1. Okay, so there's a hope that the conjunction can be a 1. x is 1, y is 0, but not y becomes 1. Then we have 1 and 1. 1 and 1 is 1. I don't even have to figure out the other part because of lazy evaluation, short-circuited evaluation. I look at the third row. Yep.
When you get not x or y, should it be not x and y?
Say it again.
The not x or y part, should it be not x and y?
Yeah.
That is correct. Thank you. Very good. I forgot about that. Yep.
You want to change it to this one too?
Oh, that's right. All this stuff is in the notes too, and actually it is correct in the notes. I just used the wrong operator.
It'll be a real-time correction.
Real-time correction. I have done it in the class too. I have done correction to my notes during the class. Okay, let's take a look at the third row. X is 1, y is 1. Well, it's a no-brainer because the first conjunction has a not y. Since y is 1, not y is 0. And with the conjunction, if one side is a 0, we don't have to look at the other side. It's 0. The other one is exactly the same thing because x is 1, not x is 0. 0 and anything is going to be 0. So we end up with 0 or 0, which means the end result is going to be 0. We have one more row to go, which is pretty easy because the last row is actually symmetric to the second row, if you think about it. So in this case, the first condition is going to be false because x and whatever is going to be 0 because x itself is 0 to begin with. But the second portion, or the second condition, or the second conjunction has not x. Since x is 0, not x is 1. And the other part is y. Y is 1. 1 and 1 is 1. So we have 0 or 1, which is also 1. So now I have just proven that this equation or this formula will do exactly what we want to do with the difference bit, which means this is a appropriate gate logic to implement the calculation of the d bit, the difference bit. Is that okay so far? Okay. Who do you think will care about this? Because most of you are computer science people. You look at this and go like, I don't want to deal with bitwise and not and or and stuff like that. I want to do a subtraction. I just want to say minus and have everything done. So who do you think will have to deal with gate logic like this? Computer engineers and electrical engineers. Okay, those are the people who design the processors or the gate logic of the processors. Those people have to look at subtraction and go, how do I boil down subtraction to gate logic? Because gate logic eventually is the only thing that the computer can do, or a binary computer these days can do. Let's go ahead and figure out what B has to be. In other words, how do we compute the borrow? Well, the borrow is actually very easy to figure out because it is 0 in all cases except for the last one, when x is 0 and y is 1. So the quickest way to get to B is to say not x and y. That's it. Now I'm not going to prove it here, but you can go back, plug in not x and y to every single row and verify that this result will end up with the value of B that we want it to be. Yep.
Excuse me, for the third row, 1, 1, 0, 0, x is 1 and y is 1. So not y is 0 and not x is 0. Because both of them have and, it's going to be 0. 0 or 0 going to be 0. Oh. Okay. Got it.
That's okay. That's all right. So this is working out just fine. Okay, if I define D to be this equation here, and if I define B to be this equation here, everything is going to work out. Yep.
That equation is basically saying x doesn't equal y.
Which one?
The equation you wrote, the first equation.
The first one?
Yeah, it's equivalent to saying x not equal y, right?
That is correct. It is also called exclusive OR. But exclusive OR is not a simple gate logic. In other words, it is not one of the available operators. and that's why we don't use exclusive OR in this case. That is, but what you pointed out is correct. It is exclusive. It is the same as exclusive OR Y. Okay, so you look at this thing here, and you look at all the things that we have talked about. What is significant about this whole class? I mean, the past 45 minutes or so. What have I just done, other than talking about third grade math and stuff?
You covered binary math.
I covered binary math, but there's one more thing that I did, like this part here, that is actually very significant. Yep.
You simplified all the logic rules.
I converted arithmetic operations into
Gate logic.
gate logic. Okay, so that is a big jump because at the beginning of the class we were all focusing on regular arithmetics. Okay, we started off with base 10 arithmetics that we all understand and we all can do. We then changed to binary, and then we explained that in binary it's all basically the same thing except that they are easier. Okay, but basically similar rules but they're still arithmetic. There's still subtraction. We are taking this value from that value. But now, I'm converting everything into gate logic. So at this point, the significant part of this point is now we can design processors. We can design gate logic to perform subtraction. Okay? If I want to draw a picture, obviously this part is going to be optional. I can draw the picture of this logic here, because I can say I have the inputs of x and y. Let's go ahead and try to implement D first. D is going to take x, is going to take the negation of y. In gate logic, a little bubble means negation. And what I want to do is to do a conjunction of these two. A conjunction looks like this. The other part is taking the negation of x. So I would tap the x line here, put a little bubble here. It becomes the negation of x. And it will take y just the way it is and perform another conjunction. I take this conjunction, I take that conjunction, and I combine their result through a OR gate. So I take the output from here, take the output from here, and put it through a OR gate. And now we have the bit that we call D. Okay? And then we have the other one. We have the borrow bit. The borrow bit is really easy because in this case it is a repetition of something that we already have. This is not x and y, and this is also not x and y. So that means not x and y is here. I just have to tap this line and call that B. Okay? And that's how we implement, one-bit subtraction. All right, take it back. This is not a one-bit subtraction. There's a name for this. This is a half subtractor because we have to apply this twice to deal with one bit. Let's go back to the math here. Okay, I'm just scrolling back a little bit. The logic of this thing here in the picture will implement this bit minus this bit, ending up with this and also a potential of a borrow. That's all we have done with these gates.
So then you have a full subtractor as well?
And then the full subtractor is a combination of two half subtractors. Are we doing okay so far with this? Sort of? No? No, this part is still okay, I am hoping. Because this part is straight out of the logic equation. So now what we want to do is we want to be a little bit lazy. We put a big box around this whole thing, and we'll call this half subtractor, HS. Okay? HS has two inputs. These are my inputs, and these are my outputs. So the question now is, how do I do real subtraction using a half subtractor? Now, obviously, a half subtractor is not enough to do real subtraction. But as the name implies, it does get half of the job done. Okay, so what do we need to do? Well, let's think about it. Let's say that we have A, B, C minus D, E, F. In other words, A, B, C is, are 3 bits, D, E, F are 3 bits as well. Okay, we have another subtraction here. We'll call this row, G, H, I, and then I, J, K, L, M, N. Okay? In other words, I have named every single bit that is involved in a 3-bit by 3-bit subtraction. Is that okay? All I'm doing is to replace actual digits with unknowns so that I can apply what we have there, to this equation. How do we get I again?
C minus F.
Okay. So now we have a half subtractor. I give C to one end, I give F to the other side, and D, the D output becomes I. Is that right? Because the D is the difference of those 2 bits. I don't quite know what to do with this little thing here first. We'll just leave it alone for now. What is the other subtraction that I need in order to end up with N?
I, 0.
I and O.
We have I and 0. Okay, this is 0. Okay. So what do I need to give to the other subtractor?
0 and I.
Okay, so we need I going back to here as my X. Okay, and the other one is just a 0, right? Because Y is a 0 here. The quantity to subtract is 0. Are we doing okay so far? Okay. What do we do with the outputs? This is my D,
It's N.
and this is my B. Oh, that's right. This is exactly just the result that we want at the very last row. What about this B and this B? I still haven't decided what to do with them. What are they related to?
They are going back.
They're not going back. They're going forward. Remember, this is a borrow from the next digit. This is also a borrow from the next digit. So these two are related. Because if you OR these two and say if any of these half subtraction ends up with a borrow, we actually do end up with a borrow. That's on my K. Are we doing okay so far? Yes?
Would the second borrow be related to J on K?
J.
Oh, wait, never mind.
No, J is like way ahead of
Never
us.
mind.
Okay. Yep.
Is the K gonna be in 0 instead of 0 for the next step?
J is
The K.
K.
K. It will gonna go to be in 0's place since the K is 1. In case of the K is 1.
K will eventually get a meaningful value, but not initially. That's a very good question. Okay, because you can see that the logic comes in multiple levels. The first level of logic would be the AND gates, and then after the AND gates have their results, then we can apply the OR gate to actually end up with a useful D bit. So as a result, the propagation of the logic of the zeros and ones changing, it will take time before N and K actually has meaningful values. From the moment you change C and F, which are the inputs into these two gates, it will take a certain amount of time before the N bit and the K bit become actually meaningful. Is that okay? Because there's a propagational delay. Every gate has a particular delay, and you need all those changes to occur over time. And that's why when you are specifying operations in the processor, they always tell you how much clock cycles are needed. Yep.
So in this case, like the number like that way, what we have first.
You mean
Where
something
that
that?
number will we have 12 or 13 minus 7. Yeah, that number. So how many half subtractor do we need?
How many?
How many of those do we need?
How many half subtractors?
Yes.
Well, that's a good question.
So
We
like
need
each
to.
one has had 2.
Yes, every column has 2 half subtractors. So we need 2 half subtractors to get to these results, okay? We need 2 half subtractors to get to these 2 results, and then we need 2 half subtractors to get to this one and the final borrow. Okay? In other words, out of this entire calculation, there's one final borrow bit that basically says, do we actually have enough value from ABC to actually have DEF subtracted from it? If DEF is larger than or equal to ABC, then this will end up to be a 1, because we ended up having to borrow from something that does not exist. Okay, very good. Are we doing okay so far with the concept? Okay, concept-wise it's okay, because the math itself is just a lot. It's tedious, but it's not, impossible. So are you guys convinced that this is actually somewhat significant? Because what we have done is we are taking arithmetic operations that we know, like subtraction and addition, and also, well, multiplication is not here because multiplication involves shifting. But with just addition and subtraction, we take the arithmetic definition and then we convert into base 2 operations. And then from the base 2 operations, we redefine the base 2 subtraction operation by logic gates. And once we convert everything into logic gates, now we can actually implement everything using electronics. And that's why this part here is important, because it goes all the way from arithmetic operations all the way down to logical operations. Yes, sir?
Is there any system that uses a different method of subtraction, or is this universal?
There are analog computers, and analog computers do not do subtraction like this. They actually have op-amps or operational amplifiers that will do real subtraction using voltages. But most of the time we don't use analog computers anymore. We use digital computers, and when we say something is a digital computer, it is actually overgeneralized. Because these days, when you're talking about a digital computer, you're also talking about mostly a binary digital computer. Everything is represented by zeros and ones. And this is why. Because we know how to deal with zeros and ones using all these AND, OR, and negation gates really, really easily. If you have base 3, we don't have a logic system that can easily deal with that. But with a base 2 or binary system, we can convert arithmetic operations into electronic circuits that can do the same thing. Yes, sir?
What's the point? What's the point of the OR gate for the 2 if the K bit is only dependent on the borrow from the second?
But there are 2 ways to generate a borrow, because you can have C being 0, F being 1, that can generate the borrow that is known as K here. You can, well, in this case, yes, you're right, because I minus 0 cannot possibly be, this has to be I, okay? N is the same as I because, it is being subtracted from 0. Or 0 is subtracted from I, so this one is trivial. But in order to make this logic cascadable, I have to write it out like this. Any questions about this? No questions? So next time I can bring breadboards and 74 XC logic gates, and we can all implement actual binary subtraction gate logic. I mean, that's exactly, if you take an electronic class or you take an electrical logic design class, that's exactly what you will do next. Okay, you will use what we call jelly bean parts. 74 HC parts are also called jelly bean parts, because one chip can implement like 4 AND gates, another chip can implement 4 OR gates, another chip can implement like 6 negation gates and stuff like that. And then what you do is you use wires to actually do all these connections. And then the input would all be toggle switches. Okay, this is a 1, this is a 0, this is a 1, this is a 1, and so on. You specify the input. The output will be used to drive LEDs. So you have a whole bunch of, you have 2 banks of switches to serve as the input. Which number is being subtracted from which number, and then you have another bank of LEDs to give you the result in binary. That's what a logic design class will teach. But since this is not a logic design class, we are not going to go there. But some of you will eventually have to take a logic design class, and you will see this again.
We'll see it harder.
You will see it harder because it will take a UC Davis professor maybe 15 minutes to go through this stuff here, and then you'll go to the lab and start to do an experiment using this kind of stuff. So this is all here, except for the gate logic stuff. The binary addition and subtraction, they're all basically there. And the summary is, it's pretty easy. Binary subtraction is easy. So the gate logic stuff is actually just kind of a little bit out of scope. But I think it is not too big of a step to go from binary subtraction and binary addition to the gate logic that can actually perform these operations as Boolean operations. Okay. Are there any questions so far? No questions? Do you want to be the person who designed the gate logic of the Pentium processor? Well, let me just, since we are digressing anyway, let's go ahead and digress all the way. Your Pentium processor is a 32/64-bit processor, which means instead of a 3-bit by 3-bit subtraction, you have 32-bit by 32-bit subtraction, right? And every time you add one column, you have to add 2 more of these half subtractors. But that's not a killer. The killer is basically these things will have propagational delay. In other words, to start with C and F and ending up with N and K, there will be a certain delta of time. Okay? It needs a certain amount of time to go from C and F as input to N and K as output. And you need N and K as output in order to finish the calculation involving B and E to come up with M and J in this case. Okay? Is that making any sense? So this is all going to be proportional. The more bits that you are subtracting, the more time it will take. Is that making any sense? It is just linear. Okay, if you have a 32-bit processor or 32-bit subtraction operation, it will take 32 times the propagational delay of 1-bit subtraction. So that means your Pentium processor is going to be pretty slow if operations are really done like this. But the answer is, nope, they're not actually done like this. Okay? In other words, they have techniques in logic gate design so that you don't need to wait for the propagational delay from earlier steps like this. Okay? But that's far more complicated than what we have talked about here. For those of you who are interested in that, I don't think anyone is really interested, but I'll show you guys anyway. I have never let that stop me from introducing topics. I think I have a note on that somewhere. There we go. If you go to module 9.5, if anyone wants to, I can link it. It won't be in your exams, okay? But I can still have a link to it. This one talks about, what is a half adder and a full adder. And optimizing a full adder for 2 bits. And we end up with, you get the idea. There are many, many inputs. X and Y's are all inputs. S for sum, carry, C for carry. Those are the output bits. So the actual logic to do it is this part here. To come up with the carry bit of bit 1, you actually end up with a fairly big equation already. So a Pentium processor having 32 bits, the equation cannot be handled by a person. It's going to be machine generated. Are you guys getting the concept? You basically have a program to generate the logic that is needed for a 32-bit by 32-bit addition and another one for 32-bit by 32-bit subtraction. Yeah, because the math involved, is really hard for a person to keep track of. But for a machine, they can actually do it fairly easily. So for those of you who are interested in getting additional understanding of gate logic when it comes to adding and not really subtracting, in this case it's just adding, go to this note here. It is just module 95 instead of the other modules. And I wrote this in 2006 when Mr. Fox was acting chair of the area. Most of you were not here at the time. How many people were here in 2006? So nobody knew that Mr. Fox used to be acting chair of the CSIT area.
Well, he told us when we were in his class.
Oh, okay. It was quite interesting. I remember it was fall. It was the fall semester, and our area dean, moved on to a VP, vice president of something in the administrative building as also interim. So when she moves over there, someone has to fill her, office. And Mr. Fox, just, said, okay, I can do that. But what happened to all the classes that Mr. Fox is supposed to teach starting Monday? Somebody has to do it. That would be me. So the Friday before instruction started, Mr. Fox and Barbara, just send me an email and say, Tech, do you think you can start teaching those classes that Mr. Fox used to teach? How many of those classes? Oh, just 3. What classes are we talking about? I can do Excel and Word. I mean, that's not a problem. CISP 400, CISP 430, and CISP 440 in the same semester. Can you do that in 3 days? Classes are starting on Monday. Yeah, I can do that. And that's why I end up with notes for those classes too. So for those of you who want to kind of have a reference of that kind of stuff, I do have those topics as well on my website. Not really relevant for this class, but I think this stuff is closely related to what we just talked about. So for those of you who want to get some additional understanding of that material, this is a good time, and you can visit my website for that stuff. So what we are at this point, because I know most of you are thinking, it's almost time to go home. I need my dinner. So do I. So the next topic, read ahead of me, the next topic on Thursday is going to be the story of registers as well as memory access. Those two kind of go hand in hand. Okay, so we are still not going to talk, but we're still not talking about assembly language programming, but we are talking about the components that you need to understand in order to write programs in assembly language. Because in assembly language programming, there's memory access, and then there are registers. So this will explain why we have registers and what happens when you access memory. Okay? I will see you guys on Thursday, so don't forget to read ahead of me. There's no new homework assignment, so take a breather. I will be at the lab if you want me to take a look at your WinSCP problem. I will be at the lab after this class.